Hey Kyle,
Hey,
how you doing?
I'm doing,
In COVID adjusted terms?
yeah.
Yeah. Uh,
How about you? Are you doing okay or?
I'm fine. I mean, we're all healthy. I'll be glad when the semester's over. I this is I'm very behind on grading. Being online is taking up an enormous amount of time. Um, I come down here. I will probably be in this chair largely uninterrupted from now until 6 or 7 o'clock. And I will be tired of having been in this chair that long. It's a little worse right now because it's our senior seminar conference is Saturday, so I'm doing practice talks in the evening. So I've had 2 or 3 hours of practice talks every night this week, and adding that on top of the rest of the day is like, but I will survive because we do that. How are your classes going?
They've been going well for the most part.
So faculty been muddling through with the whole online teaching thing.
Yeah.
Yeah. Ugh. Hello, Aaron. I do love that picture, by the way.
Thank you.
I that's from some sort of stage event. May I ask what crazy thing that was from?
I'm not entirely sure what it's from,
Oh,
but in one of my classes, we were talking about the concept of a theatrical claptrap. And so what popped into my mind was this character named Claptrap
ah,
from a game called Borderlands. And that is that character on a stage.
very cool.
Therefore, a theatrical claptrap.
Gotcha. Did you actually make that costume? Is that you in that, or did you just find the picture somewhere?
No, I just Googled theatrical claptrap, and this is one of the images that came up.
Gotcha. Okay. I've been sitting here assuming that it's you in that box all this time. So now I know that it's, well, I think I'm probably still going to assume it's you in the box just because I like that assumption.
I'm all right with that, you know?
Yeah. Yeah. Totally. 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 Uh, yeah. It must particularly suck theater, any of the performance programs. This being online has, I'm sure, been a real mess for you. Um,
It's difficult at times. We're trying to adjust. I'm in fundamentals of acting right now, and we have two scenes left. We had two scenes left of the semester to perform. The first one, we just kind of tried to make do with what we had because we had started preparing that before break. And so we just kind of did it face to face over Zoom.
right.
Um, that was kind of tricky. So this one, we found this like emergency actors pack that was made for this situation.
Cool.
So all of the scenes are like supposed to take place in a virtual meeting anyways.
Oh,
So it's
nice.
kind of working that way.
Oh, that's very interesting. So somebody's been actually written some material with the intent of it being performed in this sort of space.
Right.
Oh, cool. Well, that's a smart plan. And I would guess there'd be like significant demand for that at the moment.
Yeah, that's why we're really happy that they're just like giving it for free to people and like, hey, we understand this is weird. Take this and work with it because you can and it works and it's great. So
Very cool. Very cool. Oh, I like that idea. I'm glad that people are being creative and finding ways to deal with stuff. That's nifty.
yeah.
Um, uh, Very cool. Well, if there's ever like a public performance of anything interesting, let me know because we're stuck here watching all the random things that everybody else is stuck here watching. It'd be kind of cool to actually watch students like make some theater in a weird way. That would be fun.
Yeah.
Oh, that's very fun. Have you actually participated in any of it, Justin, or just sort of heard about it?
Yeah, I was muted. No, it's for a class for one of the people that lives here. So
Very cool.
it's for like their fiction and writing. So they're playing D&D while they're doing that, which I was like, that's pretty cool.
It is. It is. That's awesome. I'm sure that when the dust settles, there will have been some very creative approaches to certain things. Unlike, 1302, where Nick's like, well, we'll just do lecture online. But I'm sure that some people will have come up with some very cool things, ways to deal with the complicated craziness. So, yeah. Oh, we should start. It's 9:16. I was so wrapped up in everybody's fun stories. Two announcement-y things. First is I moved the first chapter 12 assignment. It was scheduled to be due Monday at 9:15, beginning of class. I moved it to Tuesday night because as I was sort of going through notes for today, it just wasn't clear to me we were going to get through everything I wanted to do today in a fashion that would be helpful, especially if the assignment was due Monday. So we'll do as much as we can today, but we may also do some of this stuff on Monday. So I moved the assignment to Tuesday night, so you've got a little more time. And you can thank, there's a handful of people that clearly started early and started asking a bunch of questions, and that helped make it clear to me that there was stuff we needed to talk about in class and that there wasn't really going to be enough time. And so everybody should be grateful for the people that started early and got in my face about like how much confusing there was. So that's been moved to Tuesday night. And then the other announcement is tomorrow, Saturday, starting at 2 p.m., is going to be the semesterly senior seminar conference. So normally this is in, like, we all get together in 2 physical rooms in the science building. And unlike a lot of disciplines where senior seminars are spread out across the semester, we run it sort of as a conference. So it's half-hour slots and we just run through everybody. And we have snacks and it's very nice. And now we're online. So we're going to be doing that tomorrow, starting at 2. There'll be 2 virtual Zoom rooms. There's going to be something like 15 students presenting. So this will go on for like 4 hours, 5 hours. You do not need to come for all of it. You don't need to come for any of it, but you can come and see, what kinds of things people are doing. And for those of you that are computer science majors, you'll get to see kind of what a computer science senior seminar looks like, at least in a COVID-19 universe. And there's a lot of really interesting topics. So I think, you could learn some cool stuff. The schedule, I think, may have just been released shortly before class. I need to figure that out. But when I have a schedule, which I should have this morning sometime, I'll post it on Canvas and on Slack, so you'll know kind of who's talking and what their topics are. And you ought to be able to sort of duck into a Zoom room, watch a talk or 2 or 4, and then bug out if you need to leave, and that'll be fine. But if you're looking for something different to watch on TV rather than Netflix, you can come to Computer Science Senior Seminar Conference, and it'll be fun. And I think we've got some cool things going on. We will not be able to provide snacks, of course, because nobody has figured out how to push food across the internet. But hopefully you can find some Triscuits and grapes in your house or some equivalent. it'd be fun to sort of tune in and find everybody with a pint of ice cream, busily working away
You
while
can't just
talks are happening.
reimburse us?
What?
You can't just reimburse us?
No, actually, I'm pretty sure that won't work.
Damn, I'm never getting my gold-plated chocolate.
Sorry, not going to happen. Not on our dime, certainly. So good try though. So that's happening tomorrow, starting at 2 p.m. Morris time, and I'll try to get the details out as soon as I have them. So the battle plan today is to do some more examples of induction. In particular, I was going to do 12.4F, which is another kind of just standard summation one. But given the timing, I'm actually inclined to skip that. And if people want, I can scan in my proof and post it online. And instead go to 12.9, which is an inequality problem, because there are a lot of questions about the inequality problems. And there often are. And so my sense is that it would make sense to get to an inequality problem right away. So I was going to do that. And then as time allows, go ahead and start one of the divisibility problems. So I was going to do 12.11. And I don't know if we'll finish both of those in the course of today or not. We'll certainly finish the first one. We may only do part of the second one. We'll see how that goes. So that's the plan. Are there any questions about anything before we launch into that?
Yeah, I wanted to ask about 5 and 6 on the quiz.
Okay.
How you handle division in those problems.
So totally. So share whiteboard. So when we say excuse me while I get the whiteboard sorted out. When we say, for example, well, if we look ahead at 12.9, at 12.13 as an example. Actually, we don't want to do that. Let's do 12.11. That sounds like more fun. So I won't do the whole proof right now, but it introduces the divisibility question. And then we can come back to this. So we have the statement in English that 4n minus 1, wow, that minus is really weird looking. 4n, oh, come on, computer. Oh, stop it. Minus 1 is divisible by 3. Which actually turns out to be an important fact in number theory and relates in some weird way to cryptography, which we will not get into. So what does it mean for us to say that 4n minus 1 is divisible by 3? It means that, well, so, in kind of simple English, right, this would mean something like the remainder of dividing 4n minus 1 by 3 is 0. But, I mean, that's true, but I'm not sure that's really helped us very much. What we really want to get to is, because we don't really, in general, we kind of want to avoid dividing and remainder stuff if we can. And so one thing to think about is when we talked earlier about x is even, right? That's the same as x is divisible by 2. And the way we actually had translated x as even is we had said there exists a k such that x equals 2k, right? What does it mean to be even? It means that we are a multiple of 2 in some fashion. And the details of what k are not important, hence we can sort of bury that in the exists. All we're saying is that there is some k where x is twice k. And so this is the general way we're going to handle divisibility. So if we come back to this guy here, this is going to be, there exists k where 4 to the n minus 1 is not 2 times k like it was over here. It's going to be 3 times k. If we're divisible by 3, then 3 times something equals our number. Okay? Why is 15 divisible by 3? It's divisible by 3 because 3 times 5 is 15. Why is 52 divisible by 4? It's divisible by 4 because 4 times 13 is 52. So there is some k where 4 times k is 52. And so in general, a statement P is divisible by Q Q translates to there exists K such that P equals K times Q. Right? So that's, in general, that's what something like this translates as. And that's true not just for numbers. So one of the exercises, 12.13, has that we're saying that x to the n minus y to the n is divisible by x minus y. And so that's going to translate as there is some k such that x to the n minus y to the n equals k times x minus y. And here k, whereas up here k is just a number, here k could be sort of a full polynomial. It almost certainly has to be. It's not going to be the case that like 7 times x minus y is going to be x to the n minus y to the n. K is going to have to be some weird polynomial. And when we talk about the divide by examples starting later today and probably continuing to Monday, I'll show you some techniques for finding these Ks and how to do these. These are not trivial, and that's part of why I wanted to push the assignment off a little bit, because we need to make sure we've got some time to talk about this in class before this is due. So Cole, did that help at all? Was that useful?
Yeah, that helps a ton, actually.
Does it? Okay.
Mm-hmm.
Wasn't clear if I was answering the right question or not. So other questions about any of this before we launch into some examples?
For those exercises, are you just not allowed to use mod and division, or?
Well, I think you could use mod, but I think you're going to find actually it's not obvious how to solve the problem if you use mod. That when you get to the, so remember we're sort of saying we're assuming P of n and proving P of n plus 1. And if you assume P of n and you're using mod, you're going to find you don't have very much to work with when you try to come here. But if you assume P of n by assuming that there is some k that works for P of n, you can use that k, you can use the k from here to help build the k you need for here. So it helps you construct the thing you need for the induction step. And like I said, we'll do an example of that, if not later today, Monday. But I think you'll find, so there are other ways to do it, but I think you'll find that this way works pretty well compared to some of the alternatives. Questions? Okay, then let us continue on with an example. So I'm going to do an inequality problem because those are always fun and confusing. And then as time allows, we'll do a divisibility problem. So the inequality problem I'll do is exercise 12.9. 12.8 is on the homework. This is pretty similar and actually has an interesting connection to 12.8, which we'll see in a second. So the thing we have to prove is to prove that for n at least 4, n squared less than or equal to 2 to the n. And this is an interesting problem because it, instead of being for n greater than or equal to 0, it's actually n greater than or equal to 4. It turns out that we can't start with the little ones. In particular, 3, this is 9, 3 squared is 9, but 2 to the n is 8. So this isn't true when n equals 3. But once you get to 4 and up, then it's true. And 2 to the n grows way faster than n squared. So once it starts being true, it will just get more and more true as we go forward. But it's not true for everything for n greater than or equal to 0. So we have this interesting starting point here being 4. And in the problem that's assigned, it actually starts at 3 on 12.8. It's n greater than or equal to 3 here. So we'll see what that means here. So we'll do a proof by induction on n. And the base case now, normally the base case is the smallest value where the thing's true, the starting point, right? If you think about the stepping stone example, it's where we begin. And normally that's n equals 0, but here it's not, because we're not saying this is true for all n from 0 up. The starting point of our journey is at 4. So our base case is actually to prove P of 4, not P of 0. And so this is a place where you have to actually pay attention to the problem to see what the base case needs to be. You can't just always blindly assume, oh, base case is 0, moving on, because sometimes it isn't. And this is one of those examples. Questions about that? This is a common source of confusion, so feel free to ask away. Okay. Then, so if we need to prove P of 4, so we need to show that 4 squared at most 2 to the 4, okay? Which is, and I'm gonna be cheap here and write this all on one line because I wanna try to save as much vertical space as I can. When you're writing these on paper, hopefully you'll be a little more generous with your paper, but I'm trying to keep as much of this on one screen as I can. So this is 16, at most 16, right? And this would be by like arithmetic. And then that's clearly true. Boom. So we're done with the base case. Does that make sense? Questions about that? Okay. Induction step. So for n at least 4, show that P of n implies P of n plus 1. Boom. So we're going to assume P of n. So we're going to assume n squared at most 2 to the n and show n plus 1 squared at most 2 to the n plus 1. Are we with me on that? Does that make sense? Is the setup, because if you're lost on the setup, the proofs are just never going to work, right? You got to be able to set them up correctly. Okay. Great. So I need to show this. I find, and your mileage may vary, but I find that on the inequality problems, it's almost always easiest to start with one side and get to the other rather than try to take the whole thing, because I find it's usually difficult to work the induction assumption in if you have both sides. So I'm going to start with the left-hand side. I don't know that I have a particularly great reason for starting with the left-hand side other than it's a side. I mean, it's a little hard to say why, you know, which of these is more complicated. They both have a n plus 1. They both have a 2. They both have exponentiation, just in the opposite direction. So I'm going to go with the left. I think, you know, you could do it either way. So n plus 1 squared is, by algebra, n squared plus 2n plus 1. Now, why did I do that? Well, one reason is I didn't know what else to do, frankly. I mean, you know, I've got this. Well, what do I do with that? Well, about all I could do is expand it. The other thing is that if I expand it, I get this n squared here. And hey, the n squared matches this n squared that's in my assumption. So it feels like, on the one hand, I didn't really know what else to do, but doing it didn't seem like a terrible thing because it brings me to something that is in my assumption. So it gives me some potential to use my assumption, because you're always looking to get from the thing you're trying to prove to some piece that includes the assumption so you can use the assumption. You should always be thinking about, how do I get from here to here? And in this case, expanding gets me the n squared here. And that seems like a good thing. Okay? Questions about that? Now, because n squared is at most 2n, and we've got n squared plus some stuff, we can say by algebra and inductive hypothesis, namely n squared at most 2 to the n, we can say that this is less than or equal to, and it's less than or equal to because this is less than or equal to, right? So I don't have an equality here. I have a inequality. And so it's critical then that I have the same inequality here, and that the direction all points in the right way. So this was less than or equal to that. So this will be less than or equal to 2 to the n. And then the plus 2n plus 1 just carries along unchanged. So this is coming from here. And then the 2n plus 1 just dangles along, waiting to be used at some later date. Okay? Questions about that? And these problems, there's often like algebra and exponentiation and stuff like that. And so starting early and asking questions about the algebra stuff when you get stuck is definitely a good thing. Because like I said the other day, this isn't supposed to be an algebra class. And so, or a pre-calc class. So if you think you're in the right place, but you're just like, I don't know how to do this step, or why this thing would be true, then definitely let us know, or let me know, and I can try to help you out. Okay, questions about where we are? Now we're aiming to get to 2 to the n plus 1. And we've got n plus 1 squared less than or equal to something, and we're aiming for less than or equal, but we want 2 to the n plus 1. Now, this, if we like look ahead a little bit, this is 2 times 2 to the n, okay? N plus, if the exponent is plus 1, we can peel one of the 2's off, and we get 2 times 2 to the n. So we'd like to somehow get this to be like this. Well, notice that this is, again, looking forward a little bit, this is this, right? 2 times something is the thing plus itself. And we have one of those right here. Right? We have a 2 to the n already. So we need to somehow relate this thing to that piece, okay? And we don't have to say they're equal, right? We actually can get away with saying they're less than or equal to, which is good because 2 to the n plus 1 is definitely not equal to 2 to the n. But if we could show that this was less than or equal to that, ooh, that would be very exciting, okay? Because that would be super useful. Now, do we have some reason to believe that 2 to the n plus 1 is less than 2 to the n? Anybody recognize this? Because I know some people have looked at it. This is actually the problem that's assigned on the homework. The homework problem 12.8 says that 2 times n plus 1 is less than 2 to the n for n at least 3. So exercise 12.8 is, your goal is to prove 2n plus 1 less than 2 to the n for n at least 3. And we can use that here because we know n is greater than or equal to 4, so it's at least 3. And we're looking for a less than or the even stronger less than or equal to. So we can say that this is less than, by exercise 12.8, 2 to the n plus 2 to the n, which is then equal to 2 to the n plus 1, and we're done. Okay. So I'm actually using the previous problem to do one of the important steps in this problem. And if we didn't have 12.8 sort of already given to us, we would then need to actually prove this. So we'd have to actually do another little induction proof to show that 2n plus 1 is less than 2 to the n. So if we needed this and didn't have it, we could do that as a lemma, as a separate proof to help us finish this proof. But in this case, because you're all doing 12.8 for me, I will just say, hey, 12.8 is true because you're all going to say it's true and show why it's true. So I don't have to prove it here. So thank you. Questions? I would think there would be several.
So can you just do as many like inequalities on the left side as you want, or how does that work?
Sure. If you have x say equal to y, less than or equal to z, less than w, equal to u, less than v, equal to p, right? As long as all of these point in the same direction, all of this would imply that x is, in this case, less than p. If any of them are strictly less than, then you're going to get a less than here. And we were trying to get less than or equal to, but that's okay, because less than implies less than or equal to. So technically what we showed here was n plus 1 squared is less than 2 to the n plus 1. And that's fine, because if it's less than that, it's certainly less than or equal to that. So we ended up proving something slightly stronger because 12.8 gave us something slightly stronger.
Okay, that makes sense.
So that, and if you're ever confused about stuff like this, if you think about it again, sort of in a number line kind of way, like think about what this sort of means. It means x was, let's pick a place for x. X was here, x was equal to y, so y is also here. Y is greater than or equal to z, so z is either here or to the left of it. Let's just say it's to the left of it for fun. Z is greater than w, that means w is definitely over here somewhere. I mean, it could be way over here, right? We don't know, but it's definitely to the left. And then u is here, because w and u are equal. And, oh, let's change this to a greater than or equal to, and let's say v and u actually happen to be the same. So v is here, and then v equals p, and p is here. And so after all of that, you know that x is, oh, I did all this backwards, didn't I? X was less than z. Ah, man. Yeah, so pretend this is in a mirror and is reversed. If we do all this, we here in this case, we know that x is clearly greater than p. And I got all this backwards, so my bad. But if you think about it on the number line, like it does kind of make sense that if we do all of this, we know at the end that x is definitely, in this case, less than p, or in this case, greater than p. Does that make sense? Does that help?
Yep, yeah, that makes sense with the picture.
Cool. Other questions about 12.9? Several people had asked questions about the inequality problems. Did this help make sense of those? We good?
How do you know which algebra to use?
What?
How do you know which algebra to use?
Well, that's a great question. All of them, which isn't helpful, I realize. So, you know, in this case, it's not obvious. Well, in this case, I started with the expanding the square of n plus 1, again, because I, didn't really have any great idea what else to do. And this got me something that matched my induction hypothesis. You know, so it's not always clear where to go with this stuff. Then, you know, here I'm using the induction hypothesis, and this is usually where an inequality comes in. So often most of the spine is equal. So this is equals, this was an equal over here. But the induction hypothesis is often the first place that the inequality comes in. And that's just a simple substitution. Now, this, I think, in some ways is the hard part. Like looking ahead, seeing that if we could turn this into a 2 to the n, we would be able to finish I think that's the not, I think that's the least obvious part of this. And in the problem that you're doing in class or for the homework, 12.8, there's going to be a step kind of like this. And that step, let me change color so we get, it stands out a little better. There's going to be a moment in that proof where you're going to want to know that 2 is less than 2 to the n for n at least 3. And I'm happy if you just assume that because Nick said so. You could actually prove this by induction if you wanted to. Like you could have yet, this proof requires 12.8 and 12.8 requires proving this. And that would probably be the technically right way to do it. But I'm okay if you're just like, yeah, fine. Nick said this is true. Alternatively, you could prove this without induction by dividing through both sides by 2, and you get 1 less than 2 to the n minus 1. And, well, actually, technically, you probably need to prove that by induction too, don't you? Yeah. So, I mean, if you really, really wanted to be super careful, you'd prove this by induction. But in an effort to simplify your lives, I'm happy if you just say, this is true because Nick said so. That's fine by me. So where I used exercise 12.8 here, you'll have a place where you'll want something like this, and you can be like, that's true because Nick told me in class, and I'm okay with that. And then the rest of it is just again, algebra and exponents, and looking ahead to where we want to go. But, there isn't like a simple what algebra to use. It depends entirely on the problem. And that's where, like, if your algebra is a little rusty and you get into it and you're like, I don't know how to, like, what algebra to apply here. How do I get from here to here? That's where I would totally like hop on Slack and ask a question. And I will certainly try to answer that as quickly as I can. So that probably wasn't a very helpful answer, Abdi. I apologize.
No, it was good. Thank you.
Other questions about this? So key things, do some kind of expansion. Whoops, undo. Do some kind of expansion, usually, then apply the induction hypothesis, typically, then maybe weird math, and then some more algebra, and then you're done. So, that's the basic plan. I realize that the devil's in the details, and the details are problem dependent, right? So there's not a good way for me to, without sort of doing the problem, sort of tell you what the details are going to be. Although hopefully this bit in green in the middle will be useful and save you some trouble. Questions about 12.9 before we try one of the divisibility proofs? Okay, very exciting. So if you understand this, 12.8 is very similar. So if you get questions about this, definitely ask. But if you get this, 12.8 is quite similar to this, okay? And I hope your write-up will be less messy and miserable than mine. Okay, moving forward. So let's do exercise. I'm going to do 12.10. Oh, no. Actually, I'm going to do 12.11. Yeah, that's what I'll do. So exercise 12.11. Now, the goal here is to prove 4 to the n minus 1 is divisible by 3 for n at least 0, right? Yeah. Okay. Proof. So to prove this, we're going to prove there exists k in the integers, if we want to be careful about it, because k can't be like a half or 2/3 or something, because then we wouldn't be getting the divisibility we want. Where 4n minus 1 equals k times 3. Boom. Okay. Does that make sense for folks? Basically repeating what we did earlier. Now, this is a little tricky, and it's going to use some rules that we didn't actually talk about. So you may remember that we had a little conversation about instantiation in meta theorem 9.16 back when we talked about for all. There's actually two somewhat similar, whoa, was that me or somebody else making that noise? Oh, that was me. I'm sorry. My textbook was sitting on my keyboard and key repeat was going crazy. My apologies if you were getting sort of weird beepings there. So there are two theorems about exist that are kind of like, in some way, instantiation in meta theorem 9.16 that we didn't talk about when we did exist, but which we now have to come back to. And in some ways, like meta theorem 9.16, we didn't sort of need it in chapter 9, but we need it now. We didn't really need these two theorems about exists in chapter 9, but we need them a lot right now. And we'll probably spend much of the rest of today talking about them, and then we'll actually maybe have a little time to start this proof, and then we'll come back and do more of this proof, finish this proof on Monday. So there are two theorems, and I'm gonna actually just put a line here, and we'll talk about the theorems, and we can come back to this if there's time. So there's two theorems that we care about here. One is 9.28, which is exists introduction. And it says that P with X replaced by E implies there exists X P. So this is sort of a weird thing. But what this is saying is if we know something is true for some particular expression, then we know there exists an X that makes that thing true, right? So if I know that Sally is in 13, let's do this differently. Let's do it more as a logic statement. So if I know in 1302 Sally, then by exists introduction, so by 9.28, that implies there exists some person P such that in 1302 is true. And one way to think about an exist statement like this is if I claim something like that is true, you might say, well, prove it. And one way I could prove it is I could point at somebody that makes this thing true. In this case, I can say, if I say there is somebody in 1302 and you say, prove it, I'm like, well, Sally's in 1302. That means there is somebody in 1302. So knowing somebody's in 1302 tells us that there exists somebody in 1302. And in a similar way, if I have, and this connects better to the theorem, if I know that 4 to the n minus 1 equals 3 times blah, 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 where that is something complicated and I don't care, that would imply by 9.28 that there exists a k, and if this is an integer, in the integers, such that 4 to the n minus 1 equals 3 times k. So if I know this is true, then I know there is some k where this is true. And how do I know that? I know it because this is the k that makes it true. Okay? So I can introduce an exists, hence the name, by going from a particular value to an exists. Okay? Does that make sense? Questions about that? And since what we're trying to prove is something like this, exist introduction means that we can get to the exist by proving something like this, that we can do something without an exist and use it to generate the exist. And that's really helpful because the quantifications sort of clutter up the world. And we could do everything by keeping them in there, but it's nice if we can sort of work without them, and then when we're in a happy place, use exist introduction to bring them into the universe. Okay? And we'll see an example of where and how we would do this in a second. Well, or on Monday. So first, are there questions about that? Now, the other one, which is, this one in some sense is kind of intuitive. The other one really makes everybody's heads hurt. And that's 9.30, which is sometimes called witness. And it says that exists X, R for the range, P for the body, implies Q, is a theorem. So this is a meta theorem like 9.16, like it's a thing outside of the game in some ways that allows us to say, if we want to prove this, that's the same as proving R and P, X replaced by X hat. So I'm going to write the X with this little hat over it. I'm going to call that X hat. This is another place where it's nice that we have the tablet and I'm not trying to type because there's just no way I can get X hat on a keyboard. Implies Q is a theorem. Oh, actually is a theorem provided X hat is a totally new variable. Oops. So this is definitely a what the heck is going on here moment. So what we're saying is if we need to prove that the existence of an X that makes some stuff true implies Q, well, if I'm proving an implication like this, one way I could do that is assume the left-hand side, right? I could assume this exists and then try to prove that Q is true. The problem is assuming it exists by itself isn't very helpful. If I'm saying, let's assume that there is somebody in 1302. Well, that's great. Well, who's in 1302? Knowing that someone's there by itself isn't super helpful. It would be great if I had a name for that person. Okay? Because then I could talk about a specific person in the class and not just, well, there's somebody, but I don't know who they are. Or if I'm saying, let's assume that there is an even number, it'd be nice if I could say, well, let's give me a name to the even number or the number that has some funky property that I care about, so that I may not know what it is, but if I have a name for it, I can at least do math on it. But without a name, it's hard to do things like algebra. And so what this tells us is that, yeah, we can just make up a new name. X hat has to be a new variable. It needs to be something that doesn't exist anywhere else in the problem. And if we do that, we're basically here saying, let's call the thing that we know exists, let's call it X hat and move on. Okay? So, and then we'll replace all the X's in R and P with X hat. And then we can assume that on the left-hand side and then try to show that Q is true on the right-hand side. Okay? So 9.30 is all about giving us a name for something when we have an exists on the left-hand side. And it turns out that this happens when we are doing the induction step for divisibility proofs like this, that the Pn is going to be an exist, right? This is sort of the P for this problem. And so assuming P of n is assuming this. Well, assuming it exists by itself isn't super helpful. So what we instead do is we assume that this is true for some particular K hat. And then we make that assumption, and then we try to prove that the right-hand side, which is the exists with n being n plus 1, is true. And we get to use the K hat in doing that proof, okay? That's all pretty abstract. We'll do examples, and there is an example in the book, but we'll do an example today and Monday, and we can do multiple examples because these divisibility problems are always a challenge. People always find these kind of tricky. But we'll need this in the induction step, 9.30, and we'll use this in the induction step and the base case, actually. So we'll use 9.28 in both of those places. So, questions? Okay. Let's actually look at an example. Now, I can't do any, oh, actually, I might be able to do the base case in the space that's down here. Let's try that, because if I can keep as much of this up here as possible, that would be nice. This is definitely a place where more board would be good. All right. So we want to show, so we need to show this with n equals 0. Okay. And by 9.28, this is true if, well, we can get rid of the exists here. So if we can find E such that 4, 0, minus 1 equals E times 3. So if we can find some E that makes this true, we'd be done. Well, this is, if we just do some math here, I'll start over here. 4, 0, minus 1 equals E times 3 is 4 to the 0 is 1, minus 1 equals E times 3. And that's by arithmetic. And that's 0 equals E times 3. So what value does E need to have? This is an easy one.
0.
Yay, good job. So that actually certainly follows from E equals 0. In fact, in this case, we could divide through, and this is equivalent to, by arithmetic, algebra, E equals 0. So we just divided both sides by 3, for example, and we get E equals 0. So we know that E equals 0 makes this true. Okay, so we know 4 to the 0 minus 1 equals 0 times 3. So that implies by 9.28 exists K in Z. And notice it is in Z because this is an integer, right? This is in Z. We would technically need to check that. 4 to the 0 minus 1 equals K times 3. So we've proven the base case. So done with base case. Done with base case. So we've proven the base case by basically using 9.28 to get rid of this stuff, then just doing some algebra and finding the value that works. And then by 9.28, we know this gives us that, and we're done with the base case. There's a lot going on there, and 9.28 is weird. So definitely feel free to like throw up your hands and be like, I need questions. Questions? 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 Okay, so we got 7 minutes. I'm going to erase the base case here, and we'll start talking about the induction step. We're not going to finish it, but we can start setting it up. And if I erase the base case, then we get to keep the 2 theorems up here, which I think would be useful. So is that cool? Anybody have an objection with that? Okay, I'm actually gonna do that. So erase. This isn't too bad. I've never erased a big chunk of stuff before, so wasn't sure how awful this was going to be, but it's not terrible. Not quite as nice as erasing whiteboard, but there we are. Boop.
At least there's no smudging, right?
That's right. No smudging whatsoever.
It'll be clearer if you spray your router with Windex.
There we go. Actually, my screen's got this little smudge right about here, which I really ought to clean off because it's slightly annoying every time I'm teaching class. But that's my problem, not yours. Luckily, it doesn't propagate. So, and I will say it's nice having like a ton of colors. I'm not sure I'm using them super well, but having a lot of colors is occasionally sort of cool. And, you know, at best we've got 2 or 3 colors in a classroom, and usually those markers are old and don't work very well. So it's, So induction step, we want to prove P of n implies P of n plus 1. So what is that? That's or exists K in Z 4 to the n minus 1 equals K times 3 implies exists K in Z 4 to the n plus 1 minus 1 equals K times 3. I got a little crowded at the end, apologies. So we cool with the basic setup of the induction step. P of n implies P of n plus 1. Now, by 9.30, we have a exists implies a something. And so we can use 9.30 to get rid of the exist on the left-hand side. So by 9.30, this is equivalent to, or this is a theorem, I'll say, that because equivalent means something else. If and only if. So R is just true here, so I can leave it out. So P 4n minus 1 equals K times 3 with, and it's the quantified variable that gets replaced by the hat thing. So K gets K hat. So we're basically saying there is a K that makes this true. We don't know what it is, but we're going to call it K hat. So we have a way of talking about it. And that implies exists K Z 4n plus 1 minus 1 equals K times 3. Boom. Okay. So that's a pretty big step. There's, you know, a lot going on there. So if you have questions, this would be a great time to ask. And so we would assume, so now assume the left-hand side. So 4n minus 1 equals K hat times 3. So I just did the substitution here. And we need to show exists K in Z 4 to the n plus 1 minus 1 equals K times 3. So now that's what we need to do to finish off the induction step. And I'll stop there because it's 10:19. And in 1 minute, we're not going to accomplish anything super exciting. I would love to have a good question right now.
So where did the K hat go?
It is right here in the assumption.
So it doesn't transfer over to the what we need to show?
No, we're still showing that this is true for K. The K hat in witness only applies to the left-hand side of the implication. So we have X here, and we have X hat on the left-hand side of the implication. Q remains the same. The right-hand side of the implies is the same on both sides of witness. So witness did not affect the right-hand side of the thing we were trying to prove.
Okay.
Does that make sense?
Kinda, yeah.
And what we'll do first thing here is we'll use 9.28 to say, well, I don't really want to do this exists. We'll just do it without the exists. And that'll give us, we'll be able to just focus on the inside of this. So we're basically using witness to get rid of the quantifier on the left side, and we're using exist introduction to get rid of the quantifier on the right side. And we'll start this at the beginning on Monday, and we'll work our way all the way through it.
Okay.
So questions? Does that make sense?
Yeah.
Sense enough? Okay, cool. I will get this posted. I will also save all the slides from this and try to share those as well on Slack, so that if you want to come back and see these slides as just static objects, you can do that, because I feel like that might be helpful here. So thanks a lot, and we will talk to you all on Monday. Have a good weekend. Hopefully see some of you on Saturday.
Nick, do you have time for a quick
Yeah, totally.
question? So I sent you 2 emails. One of them was, I was wondering if, so I just completely forgot about the quiz.
Oh, okay. Yeah, do it when you can.
Is it still accessible?
I think so. I think it would be accessible, but it would just show up to me as late, and I'll just like ignore the late part.
Okay.
If that's not true, yell at me.
Sounds good. And then the other thing is I sent you a link to a read through tonight of U of M Morris's theater program doing a play. It's about D&D. It's actually
Really?
pretty cool.
Oh, well, that's very cool. Do you remember what time the read through is?
7:30.
I will have to see. I think I may have some senior sem practice stuff that will overlap that, but I'll see if I can make that work.
I'm in the same boat. I have to work, but I really want to catch it, so I might be sneaking my phone around on the line tonight in the kitchen. So,
well, good luck.
Thank you. You have a good one.
Okay, you too. We'll talk to you later. Either Jack or Aaron have anything?
Nope, just listen to that last little bit for a second.
Cool. Jack, good? Cool. Okay, we'll talk to you folks later. See ya.